Welcome to this tutorial on model-based design for Quadcopter Autopilot, from concept to prototype. Here is the outline of this tutorial. In this session, we will explore how to perform requirements-based testing for a Quadcopter Autopilot system using Simulink. We'll cover linking requirements to the model, creating test harnesses and test cases, and running model-in-the-loop, software-in-the-loop, and back-to-back tests. In addition, we will conduct coverage analysis, check compliance with industry standards such as MISRA C, and perform static code analysis to ensure the reliability and safety of the design. This table lists several examples of system-level requirements commonly found in drone development. In this session, we'll start by using Waypoint accuracy as an example to demonstrate how to perform requirements-based testing in Simulink. Let's formalize the Waypoint accuracy requirement. In trajectory mode, the autopilot shall navigate to each predefined waypoint with a maximum Euclidean position error of 0.5 meters. To demonstrate the workflow, we begin by opening the flight control subsystem. First, we add blocks to calculate the horizontal trajectory error. Next, we create a requirement for trajectory following accuracy and allocate it to the horizontal position control subsystem. Once linked, we can see the requirement is connected to the model and the implemented status is automatically updated. We then open the test manager, where we have already created a test case under a test suite and a test file. We start by linking the requirement to this test case. Then, we specify the model under test. We add a temporal assessment to verify the horizontal trajectory error, setting the upper bound of the error signal to 0.5. We run the test case. After execution, we review the results. In this example, the test fails. By visualizing the logged signal outputs, we can see that the error exceeds the specified limit. The test manager also provides detailed diagnostics to help us investigate and debug the issue. Going back to Simulink, we can now see that the requirement is marked as tested, and its verification status is shown as fail, reflecting the test case result. Next, we will demonstrate the complete testing workflow using an example focused on the mode transition logic within the flight management system. The mode transition logic is modeled using state flow. It consists of 6 states and defines the transition conditions between them. To demonstrate the workflow, we begin by opening the flight management subsystem. First, we add 5 requirements related to the mode transition logic. To validate these requirements, we create a test harness. Since we are testing the logic, we select test sequence as the input and test assessment as the output for the harness. In the test sequence block, we define a series of steps and transitions to simulate different mode command inputs from the RC. The modes we include are armed, stabilized, altitude, position, and trajectory modes. In the test assessment block, we specify the pass-fail criteria to verify whether the system transitions correctly between modes based on the inputs, ensuring that the logic meets the defined requirements. Next, we open the test manager. We have created 3 test cases: model-in-the-loop testing, software-in-the-loop testing, and back-to-back testing. We will walk through each of these test cases one by one. First, we perform model-in-the-loop testing. We begin by linking the relevant requirements to this test case. Next, we specify the model under test and associate it with the corresponding test harness. For this test, the model is run in normal mode. Additionally, we enable coverage recording to analyze how thoroughly the test exercises the model's logic. Now we run the test. To visualize the test execution, we open the test sequence block to view the input signals and the test assessment block to observe the corresponding outputs and pass-fail results. After running the test, we review the results. This includes checking the pass-fail status, analyzing the logged signal outputs, and verifying that all requirements have been satisfied. If any test fails, the test manager provides detailed diagnostics to help identify and debug the issue. In the test manager, we can also review the coverage results. After the test runs, the state flow chart visually highlights the coverage status using different colors, such as green for fully covered, orange for partially covered, and red for uncovered logic. This allows us to quickly identify which parts of the mode transition logic were exercised during the test. Additionally, the coverage report provides detailed metrics, including decision, condition, and transition coverage, helping us assess the thoroughness of our testing and identify any gaps. To gain a high-level overview of the testing status, we use the Model Testing Dashboard. This dashboard provides visual indicators for requirement linking, test coverage, test results, and traceability, helping ensure that all aspects of the model have been adequately tested. From the dashboard, we can also generate a model testing report, which summarizes requirement coverage, test execution results, and any gaps in testing. This report is especially useful for documentation, review, and compliance with development standards. To ensure that the model adheres to industry coding standards, we use the Model Advisor to perform compliance checks. For example, when targeting embedded code generation, we can run checks aligned with the MISRA C guidelines. These checks help identify modeling patterns that could lead to non-compliant or unsafe generated code. The Model Advisor provides detailed results and recommendations for resolving issues, making it easier to align the model with MISRA C 2012 or other relevant standards. This step is essential when preparing the model for code generation and certification in safety-critical applications. As an example, we found several instances of equality and inequality comparisons on floating point values. MISRA C discourages these operations due to the inaccuracy of floating point arithmetic, which can lead to unreliable results. Next, in the test manager, we perform software-in-the-loop testing. In software-in-the-loop testing, the model is replaced by its auto-generated C++ code, which is compiled and executed within the simulation environment. This allows us to test the generated code in a controlled setting without deploying it to hardware. One key benefit of SIL testing is that we can collect code coverage results, helping us assess how thoroughly the test cases exercise the generated code. This is especially important for verifying the quality and completeness of the code intended for embedded deployment. After completing software-in-the-loop testing, we move on to back-to-back testing, where we run both the model-in-the-loop and software-in-the-loop test cases using the same set of test inputs and then compare their outputs. The objective is to confirm functional equivalence between the high-level model and the generated code. Any discrepancies may indicate modeling issues, code generation limitations, or numerical differences that need further investigation. By verifying that the code produces the same results as the model, back-to-back testing helps ensure that the auto-generated code faithfully represents the intended system behavior, which is essential for building confidence in the design before deployment, especially in safety-critical applications. By the way, Simulink supports embedded code generation using Embedded Coder, which automatically generates production-quality C++ code from the model for deployment on embedded targets. One of the key strengths of this workflow is the bidirectional traceability between the model elements and the generated code, allowing you to trace requirements and model logic directly to the corresponding lines of code, and vice versa. Alongside the generated code, Simulink produces a comprehensive code generation report that includes annotated source files, interface documentation, and call graphs. Additionally, the Static Code Metrics report provides valuable insights into the code's structure and complexity, such as lines of code, function counts, cyclomatic complexity, and recursion detection, helping assess code quality and maintainability before deployment. To further ensure code quality and compliance, we use Polyspace for static code analysis. Polyspace performs a deep analysis of the generated C++ code without executing it, identifying potential runtime errors such as division by zero, overflows, and uninitialized variables. It also checks the code against coding standards like MISRA C. For example, Polyspace can flag violations such as a switch statement that lacks a default case, which is a common issue under MISRA C. Including a default case ensures that all possible execution paths are accounted for, enhancing code robustness and predictability. To wrap up this session, we explored how to use models and simulations to perform requirements-based testing in Simulink. We covered the complete workflow, from linking requirements to the model, creating test harnesses, and developing test cases, to executing model-in-the-loop, software-in-the-loop, and back-to-back testing. We also discussed how to conduct coverage analysis, check compliance with industry standards such as MISRA C using Model Advisor, and perform static code analysis using Polyspace. I hope this session has provided you with a clear understanding of how to apply requirements-based testing effectively using Simulink to ensure your models and generated code are correct, traceable, and ready for deployment. Okay, this concludes the final session of the tutorial. I hope you now have a better understanding of how to develop a quadcopter autopilot using model-based design in Simulink. Thank you for following along, and please don't hesitate to leave your feedback or comments. I'd greatly appreciate your input to help improve future tutorials.